Welcome to Study Loop.
So in the part A of this problem, we are given an isothermal process. Isothermal process means that the temperature of the gas during the compression phase will be constant. And we can see from the formula here, this is approximately true for smaller changes in volume, since this is a heat capacity for the constant volume change, without any change in the volume. So heat capacity corresponding to the constant volume process. We see that if delta T is equal to 0, this means that delta U will be 0. So from the first law of thermodynamics, heat equals change in internal energy plus the work done. Since this is 0, therefore Q will be equal to W. And we know that the work done is negative 600 joules. So for the first part of the problem, the answer is that Q equals W equals minus 600 joules. It is negative, obviously, because the work done is as the volume decreases due to the compression of the process. So the work is being invested into the system. The heat flow is negative and decreases as the work is done on the gas. So we can say that the heat is flowing out of the gas. Now for the part B, we need to find the work, the internal energy actually, that is in relationship with the work done on the gas, but for the isobaric process. The isobaric process means that the pressure is constant, the pressure doesn't change. So here we can use it means the volume, the volume can be also considered to be approximately constant as well. So we can use that delta U is equal N times CV times delta T. Since the volume is not constant here actually, but we can approximate it for this formula. But actually, because the process is isobaric, the change in temperature will not be zero, and therefore the internal energy change will not be zero as well. So we can regroup this and say that this equals to N times the change in temperature times the heat capacity, which can further be said to be equal to N delta T group term times 5 over 2 R. This is the relationship between CV and gas constant for this case. So first we need to find and derive this term from other equations. So we can use the ideal gas equation. Ideal gas equation with the change of volume. So this is P times delta V equals NR delta T. Clearly, we have these two terms here, and we only need to move the gas constant term. So it's going to be equal that N delta T is actually P delta V over R. And notice one thing, this here corresponds to the work done on the gas, because this is the change of volume. The change of volume times pressure is the work done. So this is equal to work over gas constant. And since we know both values, we can directly substitute and say this is minus 600 joules, and down there we have 8.314 joules per mole Kelvin. So this will be just mole Kelvin units, and this is equal to minus 72.2 mole Kelvin units. And therefore we can directly substitute and say that delta U equals, now okay, we can say that this is minus 72.2 mole kelvins, and here we have 5 times 8.314 over 2 joules per mole Kelvin. You can see from the dimensions that this and this will cancel out, and we are left with joules. This is the energy dimension, so this is what we need. Placing these values into a calculator and evaluating the final quantity of the change of internal energy, we obtain that the change of internal energy will be equal to negative 1,500 joules. So the internal energy will be negative. And by this, we have solved this problem, both parts, and I hope you find this helpful, and that I will see you in another lesson.